I am Mathias and I'm going to present you here the dynamic CO₂ plume migration in a giant saline aquifer located in the Santos basin. This saline aquifer is named Ponta Aguda and is located in the southeastern portion of Brazilian coast, near the industries located in São Paulo and Rio de Janeiro state. Even if we put 3 different hubs in 3 different locations, and each one of them we inject 2 gigatons of CO₂, even that amount of mass will only cover a small portion of the reservoir because it's very large. You can see here 400 kilometers to 100 kilometers. In fact, it has almost the same area as the country of the Netherlands, and it is thick. You can see here 2,000 meters of sandstone with some portion of shale. The traditional way of predicting the plume behavior is to make the discretization of the space that we are going to study. And by doing so, we are covering an area of the size of the Netherlands with 1 kilometer tiles. You can see here a drawing of one of such tiles above the city of Delft. Inside it, you can see half of the university, TU Delft. You can see a residential area, you can see some industries and a channel. You can see even a pair of geothermal wells for the geothermal project of TU Delft. And I am going to say that everything inside this is homogeneous. Single permeability value, a single porosity value, a single pressure value. Of course, this is a simplification that will not work every time, and I need to have increasing details and increasing smaller scales so I can have the transport computation done right. So the multi-scale setup we have here is a set of consistent models going from the largest scales, that is called here S4, down to the smaller scale called S1. This index here is for the name of the power for the square kilometer area. So we start with the blocky view on the S4 scale. As you can see here, and we go to increasing details on the S3. Now we can see the heterogeneity level of the reservoir, and we can go to the project scale in which we can locate something like a dozen wells. Which is the S2 scale. So here you can see in much more details the heterogeneity of the reservoir. And now we can go to the scale that we can evaluate the effects for a single well. Here, in which we name S1. You can see here the level of details that we can cover. By doing so, we can have a great view of the global pressure propagation on the larger scales, and we can see how much it goes into details when we have the inside control volume. But as we know, the outside of the control volume do have pressure propagation as well. So we have to compute this on larger scales so we can transport this information to the smaller scale. The same goes for saturation. You can see here that the saturation is very simplified on the larger scales. On the left side you can see the plume for a dozen wells in the S4 scale, and on the right on the S2 scale. So you can see the level of details of the plume migration. Well, this is normal engineering. We must have simplifications in order to go forward. But the point here is if this is good engineering or not. A basic principle of good engineering is the robust design. So every time we simplify, we cannot reduce the security of our computations. And security in the sense of CCS is how much residual CO₂ trapping and solubility trapping I am having. So what we are going to check here? We are going to check if the simplification on the coarser models are not overstating the trapping mechanisms, mainly the solubility and residual trapping mechanisms. On the conceptual level, what we are going to think about is if I inject, let's say, 100 tons of CO₂ in a very large volume, such as the ones in S4 scale, or if I inject 100 tons of CO₂ in fine scale, it is going to be the same on the numerical side. We see here that the concentration of CO₂ inside a single cell is not the same. If we inject in a very large cell, it is 10 to the power minus 5, and if we inject in smaller cells, here represented by a TIF zone with some heterogeneity, it is going to be 3 to the power minus 3. So it's 2 order of magnitudes difference. So basically, on the left side, I can say that perhaps all the CO₂ is going to be dissoluted in water, and perhaps not all of it is going to be dissoluted on the right side. So there is a clear tendency here to overstate the solubility in coarser models. In fact, when we evaluated this for different setups, starting from the homogeneous, going to 2D section and to 3D sections of the 3D simulations of the whole reservoir, you can see that we have every time overstated the solubility trapping in coarser models. So this is a systematical problem that must be solved. We are going to check some different strategies to try to solve this, and you're going to see which one works better than the others. So we are going to make some comparative analysis of 3 different strategies. You can see here effective values, local grid refinement, and adaptive dynamic multi-level. In effective values, we multiply by alpha and beta the K values for solubility tables and length C parameters for hysteresis as a way to change the expected solubility of coarser cells. And by doing so, we can get the curves back to the expected ranges. In local grid refinement, we start from the coarse mesh and refine the cells only to get the numerical approximation better for the computations in a constant region of the model. And finally, in adaptive dynamic multilevel, we select if we run the transport equations in fine grid or in coarse grid, depending on the change of the concentration of CO₂. And by doing so, we can select if we use coarse or fine grid in the most appropriate way. You can see here the results on different simulators like CMG-Gen, in which we can evaluate effective values and local grid refinement. And in Darcy, that is TU Delft simulator, you can see the adaptive dynamic multi-level results. We cannot do so in CMG-Gen because it requires a different implementation of the solver. So we can only try this method in Darcy. So you can see here the different results and a septal range that is 1% above and below the fine grid results. In terms of effectivity, you can see that effective values and ADM works right. So we can at every time put it inside the expected range. Unfortunately, local grid refinements got mixed results. Sometimes we cannot make the curve inside the target range, sometimes from above and sometimes from below. So it's kind of difficult to rely on local grid refinement without a lot of work. Positive point for effective value is the commercial capability, compatibility. We can use effective values in every commercial simulator there is. But on the other side, it requires a lot of parameter tuning. We have to tune the parameter for each pair of coarse and fine model. This problem you cannot this is not a problem on ADM because it is general, it works at every time, and you do not need to turn a specific parameter for each pair. Because of this, it is a very positive approach on the long term, because you can use it reliably at every time. So in summary, we have seen that for CCS, coarse models overstate the trapping mechanisms, and this is not on the safe side. We must have a lot of care by doing predictions with coarse models. If we do the same for underground hydrogen storage, perhaps we are making errors on the safe side, so this can be a smaller problem. And finally, ADM is the method of choice for us because it computes the mechanism in the phi scale every time it is needed, and it provides a general way of solving this problem. So I'd like to thank you all for your attention, and you can contact me if you have any additional curiosity or any additional comment about this topic.